Welcome to the deep dive. We know you want to get the core of important ideas fast.
And that's exactly what we aim for.
Today, we're jumping into the exponential distribution.
Ah, yes. Sounds mathy, but it pops up everywhere.
Right, like the math behind stuff that just seems to happen randomly over time. That's what we're unpacking.
Exactly. Our mission really is to give you a clear picture of what it is and, crucially, when it's the right tool to think with.
Okay, let's do it. Where do we start?
Well, I think the most kind of mind-bending part is the memoryless property.
Memoryless. Okay.
Sure.
Tell me more. What does that actually mean in practice?
It means basically that the history doesn't matter for future probability.
Right.
Think about, say, a specific type of light bulb. If the model says its lifetime is exponential and it's already been on for 100 hours,
Yeah.
the chance it fails in the next hour is exactly the same as the chance a brand new bulb of the same type fails in its first hour.
Really, it doesn't get tired or wear out in this model.
Not in the pure exponential model, no.
Yeah.
It doesn't remember how long it's been working. It's kind of weird, but super important for modeling certain things.
Okay, that is interesting. Feels a bit counterintuitive for some things, maybe.
Oh, definitely. We'll get to limitations.
Okay.
But where does this randomness often stem from? It's tightly linked to the Poisson process.
Ah, Poisson. I remember that counting events in a time block, right? Like customers arriving.
Exactly. Poisson counts how many events. The exponential distribution describes the time gap between those events.
Okay, so they're two sides of the same coin almost.
Pretty much. If you have events happening randomly at a constant average rate, a Poisson process, then the time between consecutive events follows an exponential distribution. Think customer arrivals, calls at a call center, radioactive decay.
Gotcha. So the connection is that constant average rate. Now, there's usually some math notation, right? I think I saw lambda.
Yep, lambda, that's the star here. It represents the rate parameter.
The rate, so like events per hour.
Exactly. Average events per unit of time. And the neat thing is the average time between events, the mean of the distribution, is just 1 divided by L.
Oh, simple. So if lambda is, say, 2 events per hour.
Then the average waiting time between events is 1 over 2, so half an hour.
Okay. And variance, how spread out is it?
Also simple. It's 1 over squared.
Right. So high rate, high lambda means shorter average time between events and less variability around that average.
Well, shorter average time, yes.
Yeah.
Variance also gets smaller as lambda increases. Things happen more predictably close together.
Okay, makes sense. So when do I pull this out of my toolbox instead of, say, the normal bell curve, or just assuming anything could happen equally?
Good question. You use exponential when you're modeling the time until something specific happens, assuming that the chance of it happening right now is constant, regardless of how long you've already waited.
So waiting times, failure times, stuff like that.
Precisely. It's not for things clustered around an average, like human height, that's more normal distribution. And it's not for when all outcomes are equally likely, like rolling a fair die that's uniform. It's specifically for that time until event scenario with a constant hazard rate.
Constant hazard rate. That's the key phrase, linked to memoryless.
You got it.
Okay, so let's say I want to figure out the probability, like the chance my server won't fail in the next 24 hours. How does lambda help there?
So the probability of surviving beyond a certain time x is given by the formula e to the power of minus lambda times x.
Okay, E is that mathematical constant.
Right, about 2.718. So if you know lambda, the failure rate, you can plug in x, 24 hours, and calculate the probability to last longer than that.
I see. So it gives you a way to quantify that chance, but this feels a bit too perfect. Real systems wear out.
Absolutely. That's the big limitation. The constant rate or memoryless property is often an approximation. Real components age, external factors change, so the actual failure rate might increase over time.
So it's a useful starting point, but maybe not the whole story for everything.
Exactly. It models things like the useful life phase of some electronics quite well before wear out really kicks in. But it's not universal.
How is this different from the geometric distribution? I remember that involves trials.
Good distinction. Exponential is for continuous time. Think measuring time with a stopwatch until something happens. Geometric is for discrete trials, like how many coin flips until you get heads. Counting attempts, not measuring time.
Continuous time versus discrete steps.
Mhm.
Got it. So what are some classic examples where we really do see data fitting this exponential pattern?
Well, lifetimes of certain electronic components, especially early failures or during their main operational life. Waiting times in queues, assuming arrivals are random and service capacity is sufficient. Time between radioactive decay events is a textbook one.
Okay, yeah, those make sense. And if I have like a whole data set of waiting times, how do I figure out what lambda is for my data?
The simplest way, often a good first estimate, is to calculate the average waiting time from your data.
The mean time.
Right. And since the mean is 1, you just take the reciprocal of your sample mean. So lambda is estimated as 1 divided by the average observed time.
Ah, neat. So you can estimate the rate from the average interval.
Hmm.
Okay, so wrapping up. The exponential distribution is fundamentally about modeling the time until a random event occurs, driven by this constant rate lambda, which leads to that memoryless property.
That's the core takeaway. Super useful for specific scenarios like waiting times or certain types of failure analysis.
But we always need to keep in mind its main assumption that constant rate might not hold perfectly in the real world.
Precisely. Know its strengths, know its limitations.
So that leaves us, and you listening, with something to think about. Considering that memoryless idea, where in your everyday life might that assumption be surprisingly accurate? And where is it just completely wrong?
Interesting question to ponder.
Definitely. Thanks again. That was a great clarification.
My pleasure.
We'll be back soon with another deep dive to help make sense of complex topics.